Hi ladies and gentlemen, welcome to the last recorded lesson for the year. We're going to just walk through the lesson 38 homework so that you can see how I did it. If you have any questions, of course, the study group is available and you can pose any questions you want in there. And then also you'll still fill out the pre-class scores once we're completed with this. So let's take a quick look at what we have. Some good front material here from the kernel talking about how to do this exercise. And then of course the same point breakout as we had for lesson 37. I'll give you a chance to review that. No section 1 of course, and then this second section is worth 14 points. So we're starting this time with the wave equation, and the instructions tell us that we're going to use a central difference for each of the second derivatives. One with respect to t and one with respect to x. So the notation here that the kernel uses, so I do not like the superscript notation. I think it looks better and is easier to wield all in the subscripts. The superscripts become confusing, as we'll see a little bit later on. But this is all, the part of the problem setup. So as we discussed before, the g of x down here, that's an initial condition, so that's going to be substituted in for the initial velocity. And we also have a physical parameter here, which is the wave speed. And if we were just given this problem from the beginning, then of course we would substitute in our our central differences and solve for the next time step, which is just what this first component here is. This is the next time step, and as you can see, it relies on the previous time step, or the current time step where we are now, that's time step j, but then also the previous time step j minus 1. And as you well know, having gone through this, the solution to get this thing started requires us to use the initial velocity. The framework is similar to what we have done previously. As you noted, the setup of this solution is similar to what we did for the heat equation. So these first couple of lines I just put in to make the graphs a little bit prettier. Of course, clear all, close all, and then the physical constant in this case is wave speed. The computational items are all here. Remember to check that stability. That number for the wave equation, for this implementation of the wave equation, needs to be less than or equal to 1. And the grid that the kernel's chosen here, the 16 by 80 grid, puts that stability factor or stability criterion right at 1. We also have the initial and boundary conditions here, and I've set the initial condition for the parabola, and then the initial velocity is equal to just a 1/4 across the board. Boundary conditions are of course Dirichlet in this situation. So initialization, this is the same type of setup that we had for the heat equation, and just as we did with the heat equation, this is all identical. I just copied it straight from my heat equation solution. Remember, you need to have written out what your grid is so that you can keep track of what you are doing. So a lot of people kind of confuse themselves in the midst of trying to lay out the grid. We've all agreed that we're going to have x sub i's and t sub j's, and so I would stick with that I and j notation. But for example, because I choose my x's to be across the columns in this type of fashion, where this is nx plus 1, and then I choose the rows to be my t values down to t at nt plus 1, then when I run through my loops, I have my loops that are going to be for loops, but because I need to loop through the x values first, then I have i's here, but those i's don't match up as the rows for my u. Instead, they match up as the columns. So I have the I values here, and then this is a j plus 1 on this side. So yours may be the same as mine, it may be different. The point is you need to have a very clear picture of how you've set up your solution matrix so that you can fill it in correctly for the format that you have selected. So I explicitly line out how I've initialized. And then what's really different here with the wave equation is this step 2.5, where we are using the initial velocity information and a central difference here on the first derivative in order to come up with a means of substituting. And so I've switched to the subscript notation here. Otherwise, I end up with a u squared here, which is not at all what I mean, and I don't like that level of confusion, so I've just gone to all subscripts. And what I don't have in the midst of all of this is this u10, and that's where the initial velocity comes in. So solving the initial velocity central difference, which, remember, this initial velocity central difference only pertains to the very first temporal step. So that's why we have the j values fixed at 2, which would be j plus 1, because the j value we're considering is j equals 1. That's the first time value, which in this case is the time value of 0. And then j minus 1, which is a 0. And it's that j minus 1 piece, that 0 piece, that we're substituting for. So we solve this equation number 2 here. And as the kernel lays out, we just substitute that back in. We do a little bit of algebra, and we come up with this means of calculating the second step, which includes the initial condition for velocity. Again, I'm very explicit in my comments here to make sure that it's clear what I've done. So I'm filling in my second row. I'm leaving the boundary conditions alone, of course, but all the other values will be based upon this initial velocity. So this is the implementation of what we have up here, which is I'm going to include initial velocity information, but also I'm including the initial position information in order to set up this second row here. And then finally, for my loop, and we discussed this last time, it could be vectorized, or you could just loop through, as I have done here, your values in the x positions. And remember, one go back here when we're implementing this g of x portion, remember we're actually evaluating this initial velocity at the grid points. So you can't just dump an II in here. It's not the index for the loop, but rather the actual x values. So that's important to make sure that we keep that straight. And then of course here we no longer have the g, we just have the formula for the central differences that's been solved for the j plus 1 time step. And then finally we have our picture, and you should end up with this picture here. This is not a very interesting angle for this picture, so it's worthwhile to grab it, not zoom it, but grab it and rotate it around a little bit. And now we begin to see the interesting behavior of the waves given the initial velocity that we put in. So we would expect these to just be sinusoidal up and down without an initial velocity because we had a parabolic initial position. However, when we include the initial velocity, we end up with something that has this rather interesting shape to it. And we'll take a little bit more of a look at that as we go into part 2. But that's all of part 1, right? And the kernel does a nice job of just setting this up in kind of a step-by-step manner. So the second part here is doing the same thing, except we're going to set the initial velocity to 0. So we can set this initial velocity to 0 and then just rerun the code. And you'll notice that our second step here is really going to end up being the same as what we did previously, except of course the initial velocity is going to have no contribution to what we're doing. And we can run through all of the values here in our main loop in order to come up with the picture, the same type of image, and this we can take a look at when we rotate, gives us something that looks different. This is something that starts there at the top and looks very much like a sinusoidal up and down type of motion. So this is in contrast to the problem with the initial velocity, which we see from the initial condition here. Because of the initial velocity, we have actually we're going up. The string starts out moving up because of the initial velocity, even though it's displaced and ready to come back down. Whereas here, given no initial velocity, then it just immediately starts to collapse back towards its equilibrium position in the middle. So this is exactly what we would expect. I mean, from a commentary standpoint, it's extremely uninteresting, I think, at this resolution. We can easily ramp up by a factor of 10 both of the grid points and rerun. And right, this is the situation where I now want to switch from my surf plot to my mesh plot, because here all I'm seeing is my mesh. So if your mesh is black, it's just a big black blob. So let me comment this part out and rerun with a mesh plot, and then MATLAB colorizes the mesh, and we come up with something that looks much better and is easier to see. And of course the resolution here is now, instead of being 16 steps across in the X direction here, we are 160 steps across. So we have a much better resolution. And we could, of course, increase this more, which we might in just a minute. But this little piece of code here, if you want to take a look at this, this is nice because it just animates the wave equation. So that's the initial condition in magenta, and then we have this actual profile when we run with our initial condition only. So what I'm going to do is, after this finishes, I'm going to go back and change the initial velocity to what it is in the first part of the problem. So if I put an initial velocity of 0.25 in here, and then solve at my higher grid resolution, then this is the picture that we think we should have right here. And this gives us that different looking periodic wave because of the initial velocity. And when we take a look at the animation, then we have some insight into what's going to happen. So that's still the initial position, but that pushing of the string up causes it to deflect. And there's really a lot of insight that's gained by running this type of animation that does not come from looking at the three-dimensional picture. And of course we could increase the resolution by another order of magnitude, as long as we didn't run out of computing capacity. So this part B here is to double the spatial grid, and when we do that, we end up with something that looks like this, because of course we've blown stability out of the water. If we look at our stability criterion, we're way past 1, we're all the way up to 4. And so that's the conversation, right? The stability condition, our criterion, has increased from 1 to 4 for this particular situation, and we have to have, with our implementation of the wave equation the way we've done it, our stability criterion less than or equal to 1. Similar to what we talked about last time with the heat equation, the optimal situation here is to have this value be 1/2. And so we can pick a spatial grid, which is oftentimes what we do, and then just calculate how many time steps are required in order for us to be able to satisfy the stability criterion and meet the conditions of our spatial grid. So recall we did this with the heat equation. I'm just going to run this and replace the dx and the dt and the n calculations to come up with an n value. And now it's definitely going to be stable, and it's going to be built for 32 grid points. So we see we needed to go up to 227 in our temporal resolution. So this gives us the picture. Again, there's 0 initial velocity here, but this gives us the picture. And also we're getting dangerously close to not having the utility from the surf command, and it's almost time to go to use the mesh command instead. This is nice because if we want to run, so I will turn off the surf command and turn on my mesh command, and let's run this up to the 160 we were doing in the previous problem and find out how many time steps we should have. So instead of 800, it's recommending 1132 to get our optimal stability criterion. So this situation here is more accurate. as we discussed before, there's not a means of checking accuracy with our eyeball other than very crudely, which is one of the reasons why analytic solutions are important. It's important for us to gain the understanding of how accurate is this approximation really. And what's nice about a situation like this problem, we can solve for the analytic solution and actually calculate the error at every grid point and come up with a clear understanding of what the actual error is for our implementation for the numerical approximation. Finally, we have this little extra piece here. So for those of you who couldn't get this to run, apparently if you're running MATLAB from 2018 or earlier, it doesn't matter what you do. For some reason, this won't work. I don't understand what the issue is with that, but you might have to install the 2020 version of MATLAB in order to get this to run. Probably not a wise choice to do that right now. We'd hate to have you run into computer issues as we're rolling into the last week of the semester. But I will show you, I modified the kernel's implementation here a little bit just so we could see what the actual results are. What most of you saw is going to be something that looks like this, where I have magnified the amplitude of the wave by a factor of 1,000. And so that gives us a picture that looks similar to what I'm showing you here. And that's fine. It's interesting to see that waveform, but it's also not at all accurate because I've increased the amplitude by a factor of 1,000. So the actual waveform, now watch closely here, is actually not very interesting because you notice the scale in X and Y is 10 kilometers. And so in a space of 10 kilometers, a 10-meter wave is really small. And we still see the same reflection criteria, which is what's happening here. Not criteria, but result for the approximation. But that's the actual displacement, and you can't even recognize that it looks like a two-dimensional graph. So something maybe in the 100 range or 300 range gives a nice picture that isn't accurate, but is also not quite as silly as the full-blown Z displacement. And that's the end of what we have here. So this part was not scored. So the scoring is really parts A and B here for 2, and then the same thing walking through the steps for part A. So those are really kind of 7 points apiece, but remember your guiding principle for scoring is what the kernel has up here. So just a few points before I go, and some things to check off your list and make sure that you do. So you're going to score this, of course. Then you're going to fill out the pre-class scores sheet on Teams, and that needs to be done by close of business on Saturday. Whatever time you close up shop on Saturday, that needs to be done, because on Sunday I am going to accumulate all of the homework scores and provide that data to the kernel so that she can update Q2I, and you will know where you stand in the course as you're working through the final project during the last week of school. So I need those pre-class scores updated by Sunday morning. The final project, remember, is going to open on Saturday morning, and it's worth 300 points. So we misspoke. We thought that the final exam was 200, or the final project was 250 points, but in the syllabus it's only 200 points. So it's that 200 points plus another 100 from GR number 4. And finally, we will meet on Monday for our last get-together. That's T38, and we'll just talk about the course for the most part, answer any kind of overriding questions that you might have, but remember that we're on the alternate schedule of calls, so we'll be 1 hour later for that. Anyway, that's all I have. If you do have questions about lesson 38 or any of the material as you're researching, just throw it up in the study group area and we'll address it on a case-by-case basis. Thanks very much, and I hope you enjoy your weekend.